All right, we are looking at section P.2 for pre-calc today, looking at the Cartesian coordinate system. Our first objective is that we can plot points on the coordinate plane. We can use properties of absolute value, know and use the distance formula, the midpoint formula, and equations for circles. Just a quick overview of the coordinate plane. We start in this upper right-hand side with quadrant 1, and we work our way around quadrant 2, 3, and 4. Our center here is called the origin with coordinates 0, 0. This is the Cartesian coordinate plane, named after the French mathematician René Descartes. It is also called the rectangular coordinate system. All right, first example, it says plotting data on U.S. exports to Mexico. The value in billions of dollars of U.S. exports to Mexico from 2000 to 2007 is given in the table. Plot the year, comma, export value, ordered pairs in a rectangular coordinate system. So the first thing we want to do is title our graph. This would be U.S. exports to Mexico. Then we want to think of putting our axes on here. And it says that our x-coordinate should represent the years. So we're going to put years down here. And let's go, and we're starting with 2000 to 2007. So here is 2000, 2001, 2, 3, 4, 5, 6, 7. This would be 2007 here. All right. As long as you have a few of them labeled so that people can tell what increments you're using, that should be good. Then it says our y value should be our export value. All right, and that is the U.S. exports in terms of dollars, but billions of dollars. So over here we would want to say billions of dollars. And then it's a matter of figuring out some tick marks or increments for their y-axis scale. We are looking at values anywhere from a little over 97 up to our highest one looks like about 136. So we can do a couple different things. We can put a little breakdown here and start higher up, or we could say that we're going to count by tens. All right, if we go by tens, we do not need that break. It just kind of depends on how spread out you want your data. All right, so we have 10, 20, 30, 40, 50, 60, 70, 80. This would be 90 here. So if we were plotting the point, I guess we have to go a little further. 100, 110, 120. If we were plotting this first point, we would go to the year 2000 on our x-axis and up to 111.3. So we would have a point about here. Our next point in 2001 was just slightly over the 100 mark. Our third point, 2002, was at 97.5. And we would keep going. I'm not going to take time in the video here to do that, but you would plot each point on the coordinate plane. What we've just created there is a scatter plot. And that is plotting data pairs like x, y on a Cartesian coordinate plane. All right. Our second objective is to look at the absolute value. And our definition here says the absolute value of a real number suggests its magnitude or size. The absolute value of 3 is simply 3. The absolute value of -5 is 5. We are looking for the distance it is from 0. That's how it was defined in previous courses. Now we're going to look at the algebraic definition for that. And it is a piecewise function. If you remember piecewise functions from Algebra 2, that's where we split our graph into several different chunks. The absolute value of a positive number, like this 3, stays a 3. Nothing changes. So when a is positive, the absolute value of a is just a. If A is negative, like we had here, the absolute values turn it positive. It makes it the opposite of what we started with. So here it's saying the absolute value of A is going to be the opposite whenever A is negative. So if we start out with a negative number, the absolute value makes it the opposite of what it was. And our last statement says that the absolute value of 0 is 0. All right, so using that definition, we have the absolute value of -4. Since it is a negative number, we need to take the opposite of it, which turns it into just a +4. For the second one, we're taking the absolute value of an expression. And to do that, you have to look at what would the overall value of that expression be. Is it positive, negative, or 0? If we take pi, which is about 3.14, and subtract 6, we get a negative value. And when we have that negative inside of our absolute value bars, we have to make it the opposite. So we want the opposite of that quantity pi minus 6. And we could distribute that negative in. We would get negative pi plus 6. If we want to rearrange that a little bit, that's the same as saying 6 minus pi. Either of those, this one or this one, would be an okay answer. All right, before we move on, we're looking at a couple properties of absolute value. This one says the absolute value, our answer will always be 0 or positive. Question or statement 2 here says that if we take the absolute value of the opposite of a number, it's the same as taking the absolute value of the positive or the original number. In all cases, it's going to come out positive. Statement 3 says if we are taking the absolute value of a product, we can split that apart and take the absolute value of each factor separately and then multiply our answer back together. And the same here with a quotient. If we are dividing A over B and then taking the absolute value, it's the same as taking the absolute value of each one first and then dividing. All right, moving on to a couple formulas. Our next target was to review the distance and midpoint formulas. So we'll start with distance. It says let A and B be real numbers. The distance between A and B is given by this expression, the absolute value of A minus B. Now remember, it does not matter if we are looking at 2 points. It doesn't matter if we start with this one and we measure to here, or we start with this point and we measure to here. It's the same distance. So the absolute value of A minus B and the absolute value of B minus A would be the same. Inside, we'd get opposite answers, but those absolute value bars are going to make them positive. So on a number line, if we are looking for the distance between -1 and +4, just counting spaces, we would get 5 units. And if we look at our formal definition here, we're saying the absolute value of the difference between those two numbers. So -1 minus 4 would be 5. It is the same as looking at the difference between 4 and -1 in that order. All right, now, if we are looking at distance on a coordinate plane, so more of a slanted version of this, the distance between any 2 points, in this case, we're labeling them P and Q, that have coordinates x1, y1 and x2, y2. This should look familiar. The distance is the square root of the quantity x1 minus x2 squared plus y1 minus y2 squared. If we think of that in terms of a triangle, we are starting out here. We can measure this and make a right triangle. And then we know the Pythagorean theorem, right? A squared plus b squared equals c squared. So let's look at what is the distance from here to here. They have the same y coordinates, so we're not looking at how high they are. They're both equal in that case. We are looking at the distance between the x coordinates, which again, using that absolute value definition, is the absolute value of the difference between the two x coordinates. When we look at this direction, they have the same x coordinates, so we don't have to worry about that. We're comparing the y values to get a distance of the absolute value of y1 minus y2. All right, so how can we write this using Pythagorean theorem? If we call this A and B, we'll leave that D since it's already been labeled that. The value for A, in this case, the distance is the absolute value of x1 minus x2, and we want to square that since we are squaring it in our equation. Our B term, the distance between the R and the Q points, was absolute value of y1 minus y2. We need to square that. Our final answer should be D squared. All right, simplifying. When you square something, it always ends up being a positive answer. So in this case, the absolute value bars don't have to be there. We could put it back in parentheses like we're used to because squaring it's still going to make it positive. Same with this one. And then instead of having D squared, if we just want to know that distance D, we can square root both sides. And this should look familiar. This is our basic distance formula that you've used for several years now. All right, example 3. Find the distance between the 2 points. Remember, it doesn't matter which one you call point 1, which one you call point 2. When you square it, you're going to get the same answers either way. So our distance is the square root. In our first parenthesis, we want to subtract our x coordinates. So 1 minus 6 or 6 minus 1 doesn't matter. Either way, when we square it, we get 25. Our second point, we want to subtract our y values. So 5 minus 2, which would give us 3. 3 squared is 9. Adding those pieces together, we have the square root of 34. All right, moving on to the midpoint formula. On a number line, the midpoint formula is the sum of the two endpoints divided by 2. Think of averaging. All right, we're just taking the average of the endpoints. So on a number line, if we have one point at -6 and one point at +3 on a number line, the midpoint would be the average of those two endpoints. -9 plus 3 would be -6, divided by 2 is -3. That means -3 should be halfway in between those. All right, and if you were to draw it out on a number line, you can see that that's the case. Between -9 and +3, we have a midpoint of -3, 6 units from each direction. Now, if we shift that to the coordinate plane, we now have two values. We have two coordinates, x and y. So we are going to average the x's, and we're going to average the y's. All right, so if we have coordinates AB and CD, we're going to add A and C, the two x coordinates, add them together, divide by 2 to average them out. Same thing with B and D, adding those two y coordinates and averaging them out. All right, so example 5, finding the midpoint of that line segment has endpoints -5, 2 and 3, 7. So we are going to add our two x's and average them out. And then we're going to add our two y's and average them out. And simplifying, -5 plus 3 is -2. Dividing by 2, 2 plus 7 is 9. We could simplify that to be -1 and 4.5, or you can leave it as 9/2. Either way is fine. So again, when doing midpoints, think of averaging. All right. Next topic, being able to know and use equations for circles. It says use the distance formula and the figure to derive the equation for a circle. So our value for r is the distance between this point and this point. Okay? So we have r equals our distance formula. We are going to subtract our x's, so x minus h squared, plus, now we need to subtract our y values, y minus k squared. And then if we square both sides, we can get rid of that big square root symbol. And what you have is your equation for a circle. So in this case, this picture up here, our circle is all of the points that fit this equation. All right, so standard form for a circle with center at HK and radius R is x minus h quantity squared plus y minus k quantity squared equals r squared. All right, so example 6. It says find the standard form for the equation. This time we have a circle with a center at -4, 1 and a radius of 8. So this is our r value and this is h and k. So our equation is x minus h squared plus y minus k squared equals r squared. And we just need to plug our numbers in now. So we have x minus a -4 squared. Simplifying that, we probably would just want you to write x plus 4 squared. For the y values, we have y minus our k value of 1. And then r is 8, so we want to square 8, and we would get 64. So the equation for that specific circle is x plus 4 squared plus y minus 1 squared equals 64. If our center is 0, 0, then h, k are both 0. And if we plug in x minus 0 squared and y minus 0 squared equals 5 squared, we can simplify that down to just x squared plus y squared equals 25. Much more basic equation. All right, a couple applications before we finish for today. Example 7, it says, using an inequality to express the distance. We can state that the distance between x and -3 is less than 9 using an inequality. So distance, remember, was the absolute value, and it says it's less than 9. And the distance we're looking for is the space between x and -3. So remember, inside we are subtracting. We want the difference between those two. So x minus -3, we could simplify that just to the absolute value of x plus 3 is less than 9. All right. Pythagorean theorem and its converse are both true. The converse states, if the sum of the squares of the lengths of the two sides of a triangle equals the square of the length of the third side, then the triangle is a right triangle. The original Pythagorean theorem starts out saying, if you have a right triangle, then the sum of the squares of the lengths of the two sides is equal to the square of the third side. All right, so example 8 says verify using the converse of the Pythagorean theorem and the distance formula. We're going to use those two to show that these 3 points determine a right triangle. Now, if you want to sketch them out, you certainly can. All right, -3, 4 would be up here. 1, 0 would be over here. And 5, 4 would be up here. All right, so we're looking to see, is this a right triangle? All right, I'm going to call this side A, B, and C. So for A, we want the distance between these 2 points, the first 2 points in my list. So we are going to use our distance formula, subtract our x's, squared, subtract our y's, squared. Simplifying, we have -4 squared, which would be 16. Here we have 4 squared, which would be 16. Adding them, we get the square root of 32. All right, side B, this one over here. We want to take the point 1, 0 and 5, 4, and look at those two. Subtracting 1 minus 5 squared, 0 minus 4 squared. Simplifying, we have negative 4 squared plus negative 4 squared. Once again, we will end up with the square root of 32. And our third side, that uses the point negative 3, 4 and 5, 4. So subtracting negative 3 minus 5 squared and 4 minus 4 squared. This is just 0, and squaring 0 doesn't give us anything. We have negative 3 minus 5, or negative 8 squared, would be the square root of 64. All right, now it says to prove that it is a right triangle, which means this is our longest side, right? Square root of 64 is bigger than the square root of 32. So we want to check, does a squared plus b squared equal c squared? All right, so if we take the square root of 32 squared and the square root of 32 squared, do we get the square root of 64 squared? And in this case, when you square something that was square rooted, it cancels each other out. We have 32 plus 32 equaling 64, and it does work. All right, example 9, using the midpoint formula. It says, it is a fact from geometry that the diagonals of a parallelogram bisect each other. Prove this with the midpoint formula. All right, so we are looking to find the midpoint and show that it is the same for both diagonals. All right, so the midpoint, we'll start out with segment AC. So looking at this diagonal, remember midpoint, we add the x's and average them. We add the y terms and average them. Simplifying, we have a plus c over 2 and, whoops, not plus, and b divided by 2. Okay, looking at the other diagonal, it's a different color here. All right, looking at OB, we are adding our x's. So 0 plus a plus c divided by 2 and 0 plus b divided by 2, adding our y's and averaging those. Simplifying, we have a plus c divided by 2 and b divided by 2. And since they are the same, we have proved, I need some more space here. All right, since they are the same, we have proved that the diagonals have the same midpoints, which means that they bisect each other. All right. All right, our last example says, prove algebraically that a triangle determined by the following coordinates is an equilateral triangle. Equilateral means all sides are the same length. So let's start out with AB and find the length of that. We subtract our x's and square them. We subtract our y's and we square that. So in our first term, 3 minus 8 is negative 5 squared would be 25. In our second term, we end up with 2 minus 5 root 3 if we distribute that negative, and the 2 minus 2 is 0. So we really just have negative 5 root 3 squared. And if you think about it, negative 5 root 3 times negative 5 root 3 is 25 root 9, but root 9 is 3, which gives us 75. And here we have the square root of 100, which is just 10. Okay, that's our first side. All right, our second side, we can look at segment BC. We will do the same thing. We are going to take our x's, 8 minus 13, subtract those and square it. Do the same with our y coordinates. Subtract them and square it. Simplifying, we have negative 5 squared is going to give us that 25 again. In the other set of parentheses, the 2's are going to cancel out. We're still going to have that 5 root 3 that needs to be squared just like we had here with the 75. And once again, we end up with the square root of 100, which is just 10. And then our last side, we would have segment CA, square root the difference with our x's, so 3 minus 13, and 2 minus 2, the difference of the y's. Squaring each. This last term is just 0, so we really are looking at this first term, negative 10 squared is 100, which is 10 again. And since we have the same length for each side, we do have an equilateral triangle. All right. And here is your assignment for P.2.